Well, it's an enormous pleasure to be here, and there's a particular spice to it because Bob and I are indeed old friends, and to speak in a venue that is his creation is quite a treat for me. We've all benefited in New Mexico from wonderful lighting effects, and as you well know, many visual artists have been attracted to New Mexico precisely because of scenes of this kind. It's just unbelievably wonderful here in terms of light. I believe, and I hope to show you this evening, that your appreciation and mine of light and sunsets and mountains is only enhanced by knowing what light is. And to me, the fact that only 150 years ago did people finally understand what light is, having been wondering over it for 100,000 years, it's very special. It's one of the crowning achievements of humankind to have unriddled the riddle. And this evening I want to share with you what the nature of light is. We see it, we enjoy it, we have strong emotional reactions to it, but we actually now know what it is, and we didn't until relatively recently in our long history. So here you see scenes illuminated by, obviously, the sun. The sun radiates light. It's illuminating these clouds. It's illuminating those low hills. There are, of course, other ways of producing light. On the left, that's a scene from Christmas Eve, walking along Acequia Madre, and you see the farolitos. This is a cell phone tower. It also radiates stuff, but the light it emits you can't see. It's at a frequency that our eyes are not sensitive to. But both this radiation and that radiation are actually, it turns out, the same stuff. It's the same stuff. They're different frequencies, just like channel 2 and channel 6 are different frequencies, or 1,000 kilohertz on the AM band is different from 1,200 kilohertz on the AM band. That's what's going on here. The frequency of this is something like 1 followed by 15 zeros, cycles per second, and this is something like 3 followed by 9 zeros. So there's very, very different frequencies of these things, but they are the same thing, and that's one of the joys of what the discovery was in the 1800s of what light is. And in fact, the first confirmation of understanding what light is, that I'm going to try to expose to you, was actually found by Heinrich Hertz, not by producing light. They had light bulbs by that time, but he actually produced something more like what a cell phone tower emits. Now, human fascination with light goes way back, and this is the oldest image I could think of that shows how ancient this is. This is from a little over 3,000 years ago. It's the famous pharaoh Akhenaten, who was lost to history until only 100 years ago or so, because he introduced the idea of one God, the sun god, and that was such an enormous heresy that his history was obliterated from Egypt. And he did some very unusual things. All previous portraits of pharaohs, that's he on the left, Akhenaten, all previous portraits were extremely formal and very static. And here there's motion and life. He and his beautiful wife, Nefertiti, are playing with their kids. But I draw your attention to the fact that the sun, and the sun god, is emitting rays of light. And at the end of those rays, there's odd little things. I don't even know what they are. They little hands or something, but clearly the sun is reaching out with its rays and doing something to the people. And they're clearly enjoying sitting, getting the beneficial effects of that. So this is very old indeed, and it says people have always been fascinated with light. It's just so cool. Now, to explain to you what was learned about what light consists of, I want to give you some analogies or other kinds of radiating things. If you drop water droplets into a pool, something goes outward, water waves. We say they radiate away from the place where they're produced. There's a radiation. And radiation just means that, going outward in all directions. And what is it that's going out there? Well, you see the ripples going out. The water at any one of these places the water right there isn't really moving outward. And those water drops there don't go over here. Suppose there's a cork bobbing here. That cork will bob up and down as the wave passes by. But it's crucial to understand about the propagation of the radiation of waves is that the stuff at the center doesn't actually move outward. It's somehow the energy that goes outward, not the disturbance itself, not the disturbing object itself. You put a stick in the water and you jiggle it up and down, and the stick doesn't go anywhere, but at a far distance, the cork bobs up and down as a result of the propagation, the radiation of that wave outward. Another example, you clap your hands, and something goes out through the air in all directions. So I do this, and you can hear it, and you can hear it, everybody hears it. Something is radiating outward from this source of the sound. It's called a pressure wave, and your eardrums respond to that, and the eardrums respond in such a way that your brain interprets it that there's a guy up here clapping. Okay? So here's another example of radiation, in this case of sound. So two kinds of radiation. Water wave radiation, sound wave radiation. In both cases, my hands don't get to you. My hands stay here, but at a far distance, your eardrums nevertheless are affected. That's the nature of wave propagation and radiation. Light is another example of radiation. In this case, what you shake is not the stick in the water or the clapping hands. You shake an electron. Now, just to remind you quickly that we're made of atoms. Everything's made of atoms. Atoms have at their core a massive central glob of protons and neutrons. The protons are electrically charged, and Franklin called them positively charged, so we stick with that convention. And surrounding that nucleus, there's these very lightweight electrons, which are, by convention, negatively charged. If you take an electron in your hand and you shake it, it radiates something. It radiates electromagnetic radiation is the name given to it. And one of the kinds of electromagnetic radiation is the light that affects your eyes. Another kind of electromagnetic radiation is that given off by TV transmitting antennas or radio transmitting antennas. And they don't affect our eyes, but they do affect radio and TV apparatuses. So three kinds of radiation we've seen. Water waves radiating out from a disturbance in the water. Sound waves radiating out from a disturbance in the air. Light waves radiating out from what? From a shaken, charged object. Typically an electron. Why is electron going to figure so large in this discussion? Because electrons in metals, it's a very special part of metals, it's very easy to move electrons in metals. It turns out that when you bring a bunch of aluminum atoms together, or copper atoms together, to make a wire, each of the atoms gives up one of its electrons. It's no longer bound to that atom, and it's quite free to move through the copper wire. That means that if you apply some electric forces to it, you can get a current of electrons running through there. And so there's a reason why we use the word electronics. So much of the modern world is electronic in nature, so many kinds of devices, and the word comes from the fact that typically what's being moved around are electrons. And if you shake an electron, by which I mean if you change its speed or direction, which is what's happening here, right? It's moving, it's coming to a stop, it's moving, it's coming to a stop, it's moving, and it's changing direction and it's changing speed. A shaken electron will in fact radiate away from itself electromagnetic radiation that can affect a remote thing, just like the water wave could affect a remote cork that bobs on the water. So to understand the nature of this process, I need to tell you about the concept of a field. And let me just first tease you with a little image. Here is this happens to be a proton instead of electron. If I hit it a blow, that means its speed changes. If its speed changes, it's going to radiate. And the way it radiates is quite picturesque. I've stopped the motion here, but what happens with that single blow is that there are fields, electric and magnetic fields, of a rather special sort There's electric fields represented here as orange arrows and magnetic fields represented as cyan arrows, and they're at right angles to each other, and they move outward from the shaken charge at guess what speed? The speed of light, which is also the speed of radio waves and the speed of everything else that comes from shaking a charged object. So shaking charged objects does this stuff. And well, it goes out in all three dimensions, in three directions. It's a very three-dimensional thing. Now, I remind you of something you may have heard in kindergarten. Everything is made of atoms. Atoms have positively charged, electrically charged protons and negatively electrically charged electrons. And we observe, even if we don't entirely quite know what that means, what we observe is that if you get two positive things near each other, they repel each other. If you get two negative things near each other, which could be two electrons, they repel each other. If, on the other hand, you bring a positive charge and a negative charge near each other, they actually attract each other. Okay? So we say likes repel, unlikes attract. That's one of the handy phrases to remember. There is an odd thing about this, though. It's not hard to show and see that charges behave this way, but how can that be? How can an electron here affect an electron there? Well, how did shaking the stick in the water affect a cork over there and make it bob up and down? Evidently, something is transmitted outward, something. Or in the case where they're just sitting still, there's also the issue, we're not shaking anything. How did two electrons just sitting still initially, you get, oh, why do they force themselves apart? This is action at a distance. And the first person to introduce this idea was Newton, who said, I think the Earth attracts apples and moons and other planets. And people said, that's nuts. How can that possibly be? They're not touching each other. And they said, action at a distance, that's not a possibility. That's some mystical craziness. And Newton remarkably said, well, you know, I don't understand it either, but I observe that it works. If I take this hypothesis, it allows me to predict the tides and the orbit of the moon and all kinds of things. So I'm going to leave in abeyance for now why that is. Because I don't know. He famously said, I frame no hypotheses, but I at least am able to describe things that nobody else in the past had been able to describe, and I can predict things that nobody in the past was able to predict. Well, similarly with these two electrons that are far apart, how can one repel the other? It was an enormous advance in the 1800s when Michael Faraday and James Clerk Maxwell realized that you could understand this if you thought that a single charge, an isolated thing like an electron, let's say, here's an electron sitting here, and there are no other charged objects in the neighborhood. Yes, you are full of charges, but you have exactly as many protons in your atoms as you have electrons in your atoms, and so they cancel each other out in their effects. But here's a naked electron sitting here. Young people should avert their eyes. And what we say is, what Faraday saw and Maxwell exploited was, think of the electron spinning a web of interaction around it, which could affect something that came into that web of interaction. Poetically, think of the spider. The spider spins a beautiful web. It fills a lot of the space, and it's not doing anything at the moment. He's made this web. What he's hoping, or she, is that a fly will come into this web of interaction and get stuck there and get eaten. Well, that's a way these two geniuses had of thinking about action at a distance. There's no action at a distance in the case of the spider in the web. The spider spins the web. Eventually, the fly gets stuck there, and there's a rippling through the web that announces to the spider that that has happened. And so it's kind of, there's no action at a distance in a way. The spider spins the web, and the fly interacts with the web, not directly with the spider itself. Similarly, the electron is sitting here. It spins a web of interaction in all the space here. And if another charged particle comes in, it will interact with that web itself. And if it's a negative charge, if an electron comes in, when it gets near enough, it sees a sizable effect from this web of interaction, and it gets pushed away from where this electron was. If it's a positively charged particle, like a proton, it comes in, it's attracted toward that place. So it's a two-step process. One charge makes a web, and another charge interacts with the web. Now, because the World Wide Web had not been invented in the early 1800s, they didn't call it a web. They called it a field. Okay? That's what they mean by a field. And we have ways of visualizing fields. Let me show you a few examples here. Here's a positive charge, and these yellow arrows are a representation of the field that it makes around itself, called electric field. And the direction of the arrow is in the direction that a positive charge would be pushed. And how long the arrow is how strong the field is. And you see, not surprisingly, that the farther away you get, the shorter those arrows. And in fact, many of you know that the length of those arrows, the strength of the field falls off like distance squared. Double the distance, 1/4 as strong a field. 10 times the distance, 1/100th as strong a field. That's why an electron has to get kind of close in this web before it'll get caught or affected. But this positive charge makes a field around itself, which will affect any other charges come by. And you might ask, it's a reasonable question to ask, well, is this just some sort of a mathematical model of what happens, and it's just for doing the arithmetic right or something? No, the field is real. The field can be shown to be real. And that will take us a little farther away than I want to get in this talk. But the field is not just some mathematical construct. It has a physical reality just as real as the existence of the electron. And it's sitting there in space around every charge. Let's look at what a negative charge does. Suppose I had an electron. Well, it spins a web with the electric field vectors pointing inward. The arrows point inward, corresponding to the fact that being a negatively charged thing, it spun a web such that if a positive charge comes into this region, it's going to be pushed toward the electron. And if another electron comes in, it's going to be pushed away, opposite the direction of these conventionally drawn arrows in their directions. So this is a 3D representation of the electric field around a negatively charged object such as an electron. And it's really spreads through all space. So for example, here's a positive charge, and if I move that charge around, you see that at all points in the space, the field changes. So what we're doing here is we're monitoring the strength and direction of the field at a lot of different places in space, and as I move the charge around, you'll see that, of course, then, the configuration of field throughout space changes too. It's always biggest near the charge and smallest far away from the charge. You would not be entirely surprised were I to tell you, and so I will, that the changes take time. So I don't really show this in this visualization. But when I move the charge from here to there, you see that all these places the field changes, but it takes the time that light would take to get there before those changes actually happen. Now that's not going to be critical or crucial in what happens next. But I point out that the speed of light keeps coming up over and over when you think about electromagnetic radiation or electric or magnetic interactions in general. Now, that was the electric field. And a charge just sitting here makes electric field. If the charge is moving, it not only makes an electric field, it also makes a magnetic field. And it's quite a pretty thing and quite different. So here's a proton moving along at a constant speed in a constant direction. And we're not showing the electric field it makes, but it still does. The moving charge also makes an electric field. But this is a magnetic field which only a moving charge produces. And notice it has a very different character. It's a curly field. It curls around the direction of the motion of the object. Fortunately, we'll have very little more to say about magnetic fields in this talk because it turns out that they don't typically have much effect on things. They will turn out to be important companions of the traveling electric and magnetic fields that is light, but what effects they have on matter are quite minor. And so we're going to be concentrating essentially on the electric field. But why don't you at least see that? So all charges make electric fields. If it's moving, it also makes this interesting curly magnetic field. And then there's another kind of thing, which I've already alluded to. If you have an accelerated charge, that means a charge that not only has a velocity, but the velocity is changing. It could be changing in speed, it could be speeding up, it could be slowing down, or it could be turning. That also counts as a change in the velocity. If you have that condition, which is fulfilled, for example, by me shaking an electron because its speed is clearly changing and its direction is changing, accelerated charges do something very special, which Maxwell was the first person to understand. They do the following. I remind you of this picture I already showed you of the charge that was hit once, and what's spreading out is a very distinctive and unusual combination that at any point in space around this accelerated charge, what you find is an electric field and a magnetic field at right angles to each other, which is a very odd combination of electric and magnetic fields. And it spreads out at the speed of light. And in part of what Maxwell did was he took some known equations about the electric fields made by charges and the magnetic fields made by moving charges, and he put them together in a certain kind of way, and he took some numbers that were known from just measuring how strong electric and magnetic forces were, and we did the calculation with his little formula. He got a number that was 3 times 10 to the 8th meters per second. Well, that was the speed that people had already measured for the transmission of light. And at that moment in history, it was the first person in the history of the world who suddenly understood, I know what light is. I know what light is. It's this strange combination of electric and magnetic fields, which will be made by electric and magnetic fields, which will be made by accelerated charges. This was a huge event in human history, and like invention of fire. And here's another example. Very often, radio waves, for example, are typically generated by having a bar of metal, transmitting antenna, in which by applying electric forces, you force electrons this way and that way and this way and that. You're shaking electrons back and forth in this bar of metal. Those are accelerated charges. You typically have lots and lots of electrons in this metal bar, so there's many of them being accelerated, and each of them is producing stuff. And if you do it sinusoidally, what you get is sinusoidal radiation. So what we're looking at here is along a particular line of sight, we're looking at these crossed electric and magnetic fields. The electric field is the orange one, the magnetic field is the light blue one, and the crests of these sine waves move, and they move at the speed of light. And if you look at this, you can say, one of the things you could say is, this distance is called the wavelength of that sinusoidal radiation. It's the crest-to-crest distance. That's called the wavelength. And the frequency can be illustrated by the following. Let me zoom in a little bit. So if you just stand at one place, if you stand at one place in the pool of water where the water waves are coming, you will see the waves going up and going down and going up and going down where you're standing. And you don't necessarily have any sense of the wave moving, but where you are, you're going to see it going up and down. Same thing here. If you stand at this particular place and you measure the electric field there, what you'll see is the electric field points up, it gets bigger and bigger that way, and then it shrinks, and then it goes that way, and it goes that way, and then it goes that way. So notice there's 2 different ways of thinking about these sinusoidal propagating electromagnetic waves. One is to say there's a crest-to-crest distance, and that's when you're looking at the whole thing from the side. Or if you're standing at one place and just looking at the electric field at that place, what you see is it's oscillating there. And how often the time it takes to get from there down to here and up again is called one cycle of that. And how many cycles it makes per second is what's called the frequency. So 1,000 AM radio station, the electric field is going up and down 1,000, it's a million times a second. 1,000 kilohertz is a million hertz. Hertz is cycles per second, honoring Heinrich Hertz, who was the first person to produce this kind of stuff in the laboratory. So not all radiation has to be sinusoidal. You could emit a single pulse, just accelerate once, yank the charge, and then it'll go out, but it won't be followed by anything more. But very, very, very often you have this sort of thing. And the frequency will matter because what frequency you do this at determines how those waves will affect matter when they get to them. In this context, I want to show you what I consider a very pretty picture of why you can see this wall. Now, sometimes people say, well, the light from the projector bounces off the wall. But there is no physics principle about bouncing off walls. What's really going on? Well, in the projector, there is clearly a very bright lamp, probably an incandescent lamp, I'm not sure, but there's a glowing filament in there that's sending light here, and we now know, thanks to Maxwell, that what's coming here is a mixture of electric and magnetic fields in that peculiar perpendicular arrangement. So here comes an electric field, and it gets to the wall. What's the wall made of? Atoms. Atoms. And there's a heavy nucleus with some positively charged protons in it and some lightweight electrons. The electric field is going to move those charges. It'll move the protons not very much because they're so massive. It will move the electrons a lot. And because this is coming in with a field that's going this way, this way, here at the wall, at this place, the electric field is this way and that way, and this way and that way, and this way and that way, and this way and that way. So it's driving the electron nuts. Electrons push this way, and it's pushed that way, and it's pushed this way and that. What is happening to the velocity and the speed of the electron? They're changing. What does an electron do if it's accelerated? If it's accelerated, if you change the velocity of an electron, what does it make? It makes fields. It makes, in particular, electromagnetic fields. And so the oscillating electrons here radiate outward electromagnetic radiation. And so the reason you see something is because there's new light. We can call it re-radiation. So the projector makes light. That's got electric field in it. Electric fields move things, move charges, and in particular, they're going to accelerate them, and so that sends out light. And in fact, you can see light coming from there, and so can you, because the electrons that are shaken here are radiating in all directions. So this is the wave picture of the interaction of light and matter. That's what electromagnetic radiation does. It's the electric field in the light or the radio waves or whatever that does stuff to matter, and it does stuff to matter precisely because matter is made of electrically charged objects like protons and electrons. That's the picture. And notice it's a two-step thing. First you make the light is radiated, it affects things here, and they radiate. And this goes on because this actually is illuminating you, and that's why I can see you. So the electric field from there accelerates electrons in your forehead, and they radiate light, and I see that, and that's how I can see you. So this is happening all over the room, one step after another. I should mention that what I'm describing here is clearly the so-called wave picture of light or electromagnetic radiation. Many of you know there's another way of talking about light, and thinking about light, and that's with photons, as though they're little particles of light. It was in the 20th century, with the development of quantum mechanics, that we came to this amazing conclusion that it depended on how you observed the light, whether it had wave properties, exhibited wave properties, or exhibited particle properties. And this evening I'm dwelling on the wave picture because that's the one that's most appropriate for understanding most of the phenomena that I'm going to discuss. But bear in mind there is this complementary alternative description, which is little bullets called photons. And it's not in opposition to the wave picture. They're both true. And that's hard for us humans to deal with. But both these pictures, which seem totally opposite to each other, they're both true. And what determines whether light evinces a wave nature or a particle nature depends on how you observe it. If you observe it with equipment that's sensitive to waves, it acts like a wave. If you observe it with equipment that's sensitive to bullets, it looks like bullets. That's an aside. Now, how do we actually see this? I hope I've convinced you that there is electromagnetic radiation coming from here, re-radiated from the wall. But how do you see it? Well, your eye lens focuses this stuff onto the back of the eyeball where there's the retina. And in the retina, you know, there are these special chemicals, special molecules that are sensitive to light. What does that mean, they're sensitive to light? The electric field in the light can move an electron in a molecule. And it can move it in such a way as to change the conformation, the configuration of that molecule in such a way that electrical signal is generated that travels along the optic nerve to get to the brain. And the brain says, oh, the particular molecule that is in this part of the retina has fired. And so I interpret that as saying this place in the scene is lit. And so there's work done by the brain to make sense of these electrical signals. But they come ultimately, as all effects of radiation, electromagnetic will be, it comes from the electric field. The fact that there's electric field in the light is what makes it possible for the light to affect a molecule in your retina. There is also the magnetic field, but I say again, the magnetic field has very little effect on the retina. It's basically, you could just think about just the electric field itself, even though you cannot produce electromagnetic radiation without having both there. They both have to be present, they complement each other, they're traveling companions, but the magnetic field, when it gets to the matter, typically has very little effect. There are some small effects, but they need not concern us. So that's what happens. The electric field shifts electrons in the molecule, that sends a signal, and you say, your brain says, I see a wall, or I see this projector. Okay? Now, frequency affects perception. And there's a lot of different possible frequencies. Radio frequency, light frequency, the frequency of X-rays, etc. You perceive high frequency blue light differently than you perceive low frequency red light, for example. And this is very similar to the situation with sound. Low frequency sound you hear as bass. High frequency sound you hear as soprano. The bat screams at the top of its lungs. If we could hear the very high frequencies that a bat emits, way above 20,000 cycles per second, we would go mad in the summertime because the cacophony would be literally deafening. The bat has special mechanism for disassembling its ears. It unhooks the eardrum from its listening apparatus and yells at the top of its lungs with extremely high volume, so that very high volume noise will get bounced off a soft-bodied moth that doesn't reflect very much sound. And in the time between emitting and getting the echo back, it reattaches to the eardrum, so that it can hear this very faint signal coming. This is such an incredibly amazing adaptation. It's just wonderful. But we can't hear that stuff, fortunately. The bat could hear it and would go deaf if it did. Similarly, it's only been learned in the last few years that elephants have a very, very low frequency voice that they use for communicating at very long distances. It's less than 20 hertz, 20 cycles per second. And we can't hear that either. But we can, within these kinds of sounds, from elephants to bats, there's a section of that spectrum of frequencies that we're sensitive to, and within that spectral region, we can tell the difference between low-frequency musical notes and high-frequency musical notes. Well, similarly, there is a spectrum of electromagnetic radiation characterized by its frequency, just as in the case of sound. And we are directly sensitive to a very small section. So we have, starting at the long wavelength, low frequency end, we have radio waves, going up through microwaves, infrared, visible light, ultraviolet light, X-rays, gamma rays. There is no limit. This is just an arbitrary section. You can certainly make stuff at lower frequency than radio waves. For example, 60 hertz current in your home. That's running 60 cycles per second. Very, very low frequency, and not many things are sensitive to that. And out beyond gamma rays, there really isn't another name. They're just higher and higher and higher and higher frequency gamma rays. So there's this spectrum of things. And different frequencies affect matter differently. So we can't see stuff that is lower frequency than red, and we can't see stuff that's higher frequency than blue. And why is that? Well, because the molecules in our retina just aren't sensitive to those things, just as our ears aren't sensitive to the low frequency and high frequency sound. Here is an example, a homely example. Here is a little sinker hanging from a spring. If I move my hand very slowly, so very low frequencies, the thing just moves kind of with my hand. If I shake very, 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 very fast, it hardly moves up or down either, okay? But if I carefully choose the frequency of my hand, I can get a huge response out of this, huge response. So that's true with the electromagnetic spectrum. A radio tuned to 1,000 kilohertz on your AM band is very sensitive, very sensitive. You get a big, big signal from the radio for stations that are broadcasting at that frequency. And it's pretty insensitive to stuff that's higher frequency or lower frequency. So the frequency of the light, or the electromagnetic radiation, to take the broader term, affects things. And that's why you have these names, these labels. We say these frequencies down here are radio frequencies. That's a name we use because they're the frequencies that radios can pick up and process and play music to you. Next up, we have things like a section called microwaves. Well, microwave ovens, for example. And then we have infrared, and that you sit near the fire and you feel the infrared. And then comes the visible region, which is quite a small region. This is, by the way, the so-called logarithmic scale. So this is 10,000 times higher frequency than that one, and this is 10,000 times more higher frequency than that, and so on like that. So this is an incredible spread of frequencies that's being displayed here in a very compressed logarithmic way. And each of these regions of frequencies affects matter in different ways. And one of the most important ways that differs is this. Starting at a little bit into the ultraviolet region of this spectrum and above for higher and higher frequencies, this is called ionizing radiation. The shaking is so violent and so rapid, or in the photon picture, such high energy of these little bullets of light. At these very high frequencies, light of this kind, electromagnetic radiation of this kind, can actually yank electrons out of atoms. Now think chemically what that's going to do. It comes into your X-rays come into your body. It is possible for an atom to actually be split, splitting the atom. You yank electrons out of it. Now you've got a defective atom. you've got an atom missing an electron. So it's now a positively charged ion. Ion is just the name used for an atom that's lost or gained an electron. What's wrong with that? Well, an ion is highly reactive chemically because it's electrically charged. If you have two neutral atoms near each other, each with their normal complement of electrons, they don't interact very strongly electrically because they're both balanced. Remove one of those, you now got a positive ion here, and necessarily there's some negative charge somewhere else. It's going to be strongly attracted to other matter. It's highly chemically reactive, and it can damage you. And that's why we try to limit as much as possible the use of X-rays to truly needful situations. And for example, dental X-rays have gotten lower and lower and lower in their dosage by having more and more and more sensitive films and so on, precisely because of the dangers of overuse of X-rays. When I was a kid, I'm only 25 years old, but I had a hard life. But when I was a kid, every shoe store of any merit, remember these? They had these wonderful X-ray machines, and you stuck your feet in. Most of you are too young to enjoy this. You stuck your feet in this machine, and you looked down into this scope, and you could see your toes inside the shoes and see whether they fit in the shoes. It was great. It was wonderful, and it was very dangerous. And that's why I no longer have feet. So ionizing radiation is serious, and in ultraviolet, the main danger is just sunburns. But it's my understanding that part of the UV spectrum that gets through the atmosphere to here at Earth's surface actually can be somewhat ionizing and may contribute to skin cancers as a result. So skin cancer, as we know, is a problem here at 7,000 feet. And part of that is because some of the UV is actually ionizing radiation, if I understand correctly. Does that match your perception, Bob? X-rays certainly are ionizing, and gamma rays are highly ionizing.
Excuse me, I have a question.
Yes, please. Oh, sorry.
How does this fit in when you smell the rain? It's like lightning, and you can smell this.
Yeah, in lightning there is production of ozone, O3. Okay. O3. And O3 has this very distinctive effect on your nostrils. It smells like electricity.
Yeah, right. Is it ionized particles, or is it?
What happens is that in the lightning discharge, there are chemical reactions that occur that produce this unusual species of O3. So O2 plus I suppose it's O2 plus O2 gives O3 and a single oxygen atom, I'm guessing. And O3 is highly reactive, and it has this acrid smell. And we associate with electricity because you tend to smell it near sparks of any kind.
Mm-hmm. Thank you.
Yeah.
You might point out that the lower the frequency, the lower the energy.
Yes. So if Bob reminds me to say this, in the photon picture, the bullet picture of light, what this spectrum is bullets of this light. Each bullet is very weak. Up here, each bullet is very strong. And in between, they're of medium grade. So one of the ways of thinking about ionizing radiation in the bullet picture, the photon picture, is to say photons with this higher frequency have higher energy, more and more energy as you go to the right on this diagram, and those bullets of energy deliver to an atom enough energy to knock an electron out. So that's, when you get up in this area, the photon picture is typically more useful than the wave picture. And down here, it's usually the wave picture that's more useful than the photon picture. But that basically has to do with how these different frequencies interact with matter as to which kind of behavior is evinced by the light when it hits something. And then there's an important area down here, and it's all kind of in this region here, the so-called microwave region. Here you have the upper level radios, FM, TV, Wi-Fi, cell phones, cell phone towers, microwave ovens. They're all kind of in the same box. They're all about, well, there, where I pointed to it. And I remind myself of, here is what you would get from, this is what the radiation looks like coming from a radio antenna or a cell phone tower antenna. you're shaking electrons up and down in that metal bar, and spreading out from there are these waves. Where I've suppressed, I'm not even showing the magnetic field, I'm just showing the electric field. If this, let's suppose it's a radio station. If you put your radio here, it has a little piece of metal as an antenna, and in that piece of metal, the electric field is driving electrons back and forth in the metal, and that constitutes a fluctuating voltage from one end of that piece of metal to the other, and your radio can then detect that and filter it out and play you the music or the talk show. So that's what the radiation from TV and radio antennas looks sort of like this, and it spreads out in all directions, just in the directions I've shown. If I showed it in all directions, you couldn't see anything. That's a problem in the representation. I want to emphasize, because the word radiation is so scary, it's important to understand that nuclear radiation and electromagnetic radiation are not necessarily the same thing at all. Almost all nuclear radiation, which corresponds to some change in the nucleus of the atom, not moving electrons, but changing the nucleus itself in a nuclear reaction, almost all those radiations are in fact ionizing. And they can emit chunks of matter, mainly electrons and alpha particles, which are 2 protons and 2 neutrons. It's the nucleus of helium atom. And they can also emit electromagnetic radiation, typically above the ultraviolet, typically X-ray or gamma ray region. So nuclear reactions do produce ionizing radiation. I guess there must be some cases of producing non-ionizing radiation, but it's a little hard to come by. So nuclear radiation is rightly feared, and you want to make sure that you don't eat plutonium, stuff like that. But it doesn't have anything to do with electromagnetic radiation. And my perception is that for many people who have not heard this talk, they're commingled. Radiation is bad. Well, then I like sunlight. And sunlight is electromagnetic radiation. So radiation, I repeat, just means radiating out from a source. That's all it means. And even in the nuclear radiation case, that's what it means. Something happens to this nucleus and stuff radiates out from there. So keep in mind the difference and distinction. Now, frequency is not the only thing that matters. Different kinds of things respond differently to different frequencies of electromagnetic radiation, but the power also matters, which is energy per second, watts per second, energy per second, watts. So the thing to know about the power radiated by devices, radio antennas for example, is that when you double the distance, the power goes down by a factor of 4. You go 10 times the distance, the power drops by a factor of 100. Why is that? Well, it's radiating out, and the area of a sphere grows proportional to the square of the radius of the sphere. And so you got all that power now spread over a much larger and larger and larger surface area. And so at any particular place, per square meter or something, the amount of power delivered there necessarily goes down. So we have TV transmitting antennas on top of the San Reina Cristos, and they are irradiating us right now, but not very much power, right? Because we're so far away, we're like 10, 15 kilometers away. So bear in mind that frequency isn't everything. The power also matters. A stronger source produces stronger electric fields where you are sitting. Here are some examples of power. Typical power for TV transmitting antennas depends typically on their frequency, and the reason for this is that the FCC lets you run a UHF antenna at higher power than a VHF one because the UHF one has a shorter range, it turns out. And so you can get up to 1,000,000 watts for a UHF transmitting antenna. Another example, a homely example, most of us have microwave ovens. Typical rating is like 1,000 watts or 1,200 watts. Another example is sunlight. When you're out in the sun on 1 square meter of area, so about that big, that receives on the order of 1,000 watts also. So think of it as a microwave oven. And that's why people try to make solar ovens of various kinds. So that's the power issue. Now, one of the things that's of vital interest to public debate here in Santa Fe and elsewhere is, what about these new cell phone thingies and their cell phone towers? Well, I hope from what I've shown you so far, you'll have a better way of thinking about how this all works. The first thing to know is that the cell phone network is an unusual one. It's designed to have cells. What's a cell? It's a relatively small part of a city or countryside served by a cell phone tower that is talking to the cell phone users nearby and getting messages from them to pass on. For that reason, the cell phone tower is a very weak transmitter. They're typically about 100 watts. It's like having a 100-watt light bulb. And they are transmitting at frequencies something like what you have in your microwave oven. But the microwave oven is 1,000 watts, and this thing starts out at 100 watts, and as soon as you get a little ways away from it, the power level is extremely small. So the way to think about cell phone towers is they are extremely weak by design, because they want this tower to deal two-way radio communications with the cell phone users, a limited number of them. And if you pass out of this region, you get picked up by the next cell, the next cell phone tower, so that no cell phone tower has to handle very many customers simultaneously. So by design, these are very, very weak transmitters. And that's important to understand. These are, if you, well, I have a little calculation I'll show you in a moment. Microwave ovens are pretty high power things, but they are sealed, right? And there's even an interlock that you can't open the door and stick your head in it and try to commit suicide that way because it won't run. There is some leakage. There is some leakage from a microwave oven, which runs at frequencies similar to the cell phone network and to television and so on. The cell phone, in my own kitchen, in my home I have Wi-Fi, so I can move around the house and connect to computers of various kinds wirelessly. If I turn on my microwave oven in my kitchen, it interferes with my Wi-Fi and I can't use the Wi-Fi because the tiny, tiny permissible leakage from a microwave oven, and it's a new one, swamps the Wi-Fi, which is an even weaker one. Now, how can these signals be so weak? How can we even do anything with them? The exquisite sensitivity of the modern cell phone. This thing has very, very high sensitivity, and it can take a very, very, very weak signal from a cell phone tower, or, unfortunately in my case, my microwave oven, and magnify that in such a way that we can do useful things with it. So these are all very, very weak things. I made this rough calculation, and I don't hold by the details, but there are TV transmitting antennas on top of our mountains. If you work out from the power that they emit, which is probably on the order of a few 100,000 watts, here where we're sitting now, we're being irradiated by those antennas at a level that's comparable to having a cell phone tower 200 meters away. So a lot of experimentation has already been done on us for the last 50 years, that we've been receiving from TV antennas, transmitting antennas, AM, FM, the leakage from microwave ovens, all of that stuff has been present here for a long time, and that's why things are going so badly now. Years ago, the New Republic said, has anybody noticed how bad things have gone since people started saying, have a nice day? So the great experiment has already been performed on us. We have been living in a rich world of electromagnetic radiation for a long time now, and not just from the sun, but also from all these devices that have been sending stuff to us. And I've never heard anybody express any concern about the leakage from microwave ovens, which is comparable to all these other very weak signals.
They do it FDA.
Pardon?
They do it FDA, they worry about that.
Okay, and the federal government sets standards for how much leakage is permitted. Yeah, exactly.
Yes,
Yeah, that's right. Now, some people are sensitive to either transmissions from cell phones or from cell phone towers. I want to make it clear there have been a lot of studies trying to determine how that sensitivity works on the part of those who are sensitive. And what's been found is that if you do truly blind studies where the person does not know whether the thing is turned on or turned off, even the sensitives cannot tell. The insensitive, they never tell, but the sensitive can't tell either. So that says it's not a real effect. It's been suggested this is something called a nocebo effect. You're familiar with placebo effect, which is still being studied because we don't understand it, but it's certainly true that if you give somebody a pill that will make them better, they start feeling better, even though it was sugar or something. Now, sugar would make me feel better, but so as far as we can tell, no human is sensitive to this stuff, and that makes sense because the signals are extremely weak, and they're in a part of the frequency domain where we don't have any receptors for that kind of stuff. Nevertheless, there is continuing angst about this, in part because other experiments have shown that the pain the sensitives feel is real, in the following sense. This is a very telling experiment. Sensitives and insensitives, people who thought themselves sensitive or thought themselves insensitive, were put into a functional MRI device where they could watch brain activity in various parts of the brain. This is a modern technique for understanding what parts of the brain are active under certain conditions. A cell phone was placed right beside the person's head, and then they were told when it was on and when it was off, and we looked at the MRI images to see what sections of the brain were activated or not. For the non-sensitives, there was no difference whether the phone was on or off. For the sensitives, when the phone was on, their pain centers lit up strongly. Just the same pattern they would feel with any other strong pain. And they felt real pain. The pain was real, but the cell phone was never turned on. Okay? So I have a lot of sympathy and empathy for the sensitives because they clearly are bothered by this, but it's not the cause. The cell phone isn't the cause. The cause is that I have this nocebo effect. I expect to be harmed, and so I feel harm. So there's a kind of a serious ethical question because it's not like they're imagining things. They're experiencing this real pain as seen in the MRI study. And I want to finish by saying the following. You can find on the web a lot of studies that show very serious effects of cell phone towers and cell phones. There's article after article from all over the world. Well, that should worry us all. However, each of those studies is necessarily limited. And there are issues of sample bias and all kinds of statistical issues, including, importantly, no one thinks it newsworthy to report a case where after the cell phone tower was installed, the leukemia rate dropped. This is not newsworthy. So there's already a bias in reporting. In Scotland, they installed a cell phone tower. Last year we had 1 brain cancer, and this year we had 3. See, it went up by factor 3. There's a lot of those kinds of reports, but not the other. So is there a way you could do something more global that looked at the entire population? You didn't have to select or anything. And yes, there is. And a paper by people at the National Institutes of Health, and I'll show you the reference in a moment, put together the following data. This is publicly available data. The lower graph is the number of brain cancers per 100,000 Americans per year, starting in 1977. So this is brain cancers. The black is all races, the white is whites. Whites seem to have slightly more, although I'm not even sure I don't know how to think about it. But here it is. So something like 6 people out of 100,000 every year get a brain tumor. And this lumps together all kinds of brain tumors, but the authors are careful to say, and all of them have the same trends. Okay? They think they see a slight increase here around the late 70s, early 80s, which if it is a real increase, if it's statistically valid, they point out it could be better diagnosis because the real diagnosis for a brain tumor is MRI, and MRI is relatively new technology. So there could have been underreporting before that. And I will mention as an aside, despite being only 25, when I was a kid, death was shameful and cancer was not talked about. Cancer was very shameful. And so it was absolutely certainly way underdiagnosed because you didn't want it known that there had been a death from cancer in your family. I think it was tied up with the American fear of death itself. And cancer is a particularly nasty one. But that was real. So maybe there's a little rise there due to better reporting. Here it looks to me pretty flat. You could say maybe there's a little downturn here. This goes to 2006. There is some more data that was not covered in this paper, and it looks pretty much the same. Basically, you don't see much change. Starting back here, people started subscribing to cell phones. And that is the number of subscribers in the United States in millions. And it's amazing that by 2006, it was up like 225 million, and there are only 315 million of us. I think some people carry on several of these. And the key thing is, this is a global measurement. If the cell phones were at least immediately having strong effects on brain cancers, we should see a major change in the incidence of brain cancers, and we do not see it. It is not there. It's interestingly, how much time? You need to change your...
What was that?
But,
I didn't hear that. Women, what happened? Women in their
I'm sorry, say again?
Could you say again, women in their 20s?
Women in their 20s, ages 20 to 29. However, within the cancers that they had, the rise was limited to one kind of cancer, brain cancer, in the forehead. Not here, not where the cell phone would be. So if you slice the data 17,000 ways and the average is level, necessarily some things will be higher and some things will be lower. And the term is used cherry picking if you just pick the ones that prove your own thesis. So you can certainly find all over the world places where the incidence of brain cancer has gone up, and you will not hear about the places where it went down. And you don't hear enough about the fact that in all of the United States it stayed constant. Now, the authors point out that a possible thing is that, well, the effects won't be seen until 20 years from now when all these people who use cell phones or were subjected to cell phone tower radiations got cancer then. Well, possibility. However, as they point out, there's been just as much hue and cry about the startling increase in brain cancers now. And as they say, you can't have it both ways. If it's causing brain cancers now, then this data says no, it's not. If it's to be happening in the future, well, we don't know, but almost everything of this kind, these are not diseases of aging, there's something that happens now. Maybe there'll be further effects later. This, together with the fact that prior to this time, we've been irradiated by all this other stuff I've pointed at, like microwave ovens and what have you. So I don't see any evidence that I can take as credible to say that there's any issue with cell phone towers or with cell phones. It's just not there for me because of this kind of a study, which is truly global in its coverage. Here is a reference. I don't know if anybody would want that long URL. Can this be at the Alliance website maybe, Bob, afterwards? Okay. It's a freely available article by people at the National Institutes of Health. And finally, I want to return to my village in Scotland, where last year, I'm making this up, but I've seen lots of reports that are of this kind. Last year, before we had a cell phone tower in our village, there was only one childhood brain cancer. And this year, there were 3. So putting in the cell phone tower tripled the number of brain cancers that kids suffered here. Well, statistically, 3 and 1, oddly enough, are essentially the same number. Let's suppose you never put in the cell phone tower. If you had 1 brain cancer this year, The next year you might have 2, the next year 0, the next year 3, the next year 1, the next year 0, the next year -2. Well, no, not that. So you look over time, and there's some average level. Let's say the average is 2. But that's an average of 1s and 3s and 4s and 0s and what have you. There is a simple rule of thumb that I wish were taught in the first grade that is unfortunately not the parlance of all educated Americans, and it's this, but I'll say it in words. If on the average you are getting 2 brain cancers per year, with some necessary fluctuation, some years there aren't any and sometimes there are 4 or something, you can expect 2 plus or minus the square root of 2. The square root of 2 is 1.4. So roughly speaking, you shouldn't be surprised if some years it's 3 and some years it's 1, and if many years it's 2. You would be surprised if it jumped from 2 to 76, because that's not like 2 plus or minus 1.4. So this square root of n is a very important and very useful rule of thumb for judging things. And I go nuts every time I see a newspaper article of the following kind. Last year in our county there were 100 murders. And this year there were only 97 thanks to the good work of our sheriff. Well, notice that 100 plus or minus the square root of 100 is 100 plus or minus 10. 2/3 of the years you're going to be within the range of 90 to 110. 100 minus 10, 100 plus 10. And in fact, 95% of the times it's going to be between 100 and 120 and 80 to 120. And the other side of this is, last year there were 100 murders in the county. This year there were 104. And we're very concerned about this, and we've got a special task force to study it. Well, yes, we all want to reduce murders. But not for this particular region should you be particularly anxious. So that, anytime you see something that says it's gone up by a lot, remember this little rule and ask yourself, does it pass the square root of n test? Now, caution. If last year there were 100 murders and this year there were 170, but the 70 extra ones were due to one serial killer, then the square root of n thing doesn't apply. It applies to things where they're sort of independent one event from another. But if you've got a serial killer who comes in, or you've got a massive traffic accidents that kills 75 people in one crash, that's not in this framework. So if you'd like to know more about the kinds of stuff I get involved with, just Google my name instead of giving URLs. I'm involved with 3 major things. With Ruth Shabai, who's also my wife and a physicist, we've made an introductory physics curriculum that you can read about that's being used in this country and a few places abroad. And we're also involved with 2 remarkably easy to use 3D programming environments, and I encourage especially the young people in the audience to go take a look. So Google Bruce Sherwood and read about VPython and GlowScript. It's an amazingly easy way to write little programs that do 3D animations. And with that, I encourage any and all questions, and thank you very much for coming. And I see I ran way over.